Hello everyone, this is my final project presentation for DIGA620. So the purpose of this project is to build a data warehouse of historical weather data that can be queried and used to build custom reports and dashboards for farmers depending on their location. So we have some weather data, we need to build a data warehouse, and this data warehouse has to be useful for dashboarding and querying so that farmers can make sense of and use the information. Data source is the environmental or the National Centers for Environmental Information. They have an API of weather data from lots of different weather stations. The API documentation can be found at that URL and cdc.noaa.gov. It's the V2 of their web services. That's the API URL, and they have multiple endpoints for this particular data source for weather data. But the data endpoint itself, DATA, data in place of endpoint, contains the actual weather data. So the idea is we're going to take that weather data and convert it into this data warehouse star schema here. We have weather facts, which is our main weather table with our weather information with a date, the ID of the station, and the temperature, min, max, and precipitation. We have a time dimension as well, uh, which has a foreign key to which has a sorry the date in the weather facts has a key connecting it to the time dimension table. Just contains some basic time information, and we also have a location dimension table expanding on some fields from the station ID. So this is a prototype. A prototype has been built, and in this presentation we're going to outline the prototype, what's going on, and what has been built, and then what are the future improvements, future next steps to make this into a full production system. So this is the project directory. There's just a file with some documentation, programs, data files in it that kind of outline what has been done so far. We have assessing data quality. This is the Jupyter notebook, just overviewing those three tables that were created, assessing their data quality. We have a target schema, data warehouse target schema in Excel, description of the data warehouse schema, more detailed than just that image you saw, a full-on report with a more detailed information in this presentation on the project, location dimension to geojson.py, just a Python program that converts the location data into GeoJSON format, location dimension.csv, a CSV of the formatted location dimension data, location dimension.geojson, a GeoJSON file of the location dimension data, and then NOAA API data processing.py. This is the main program of this project that both retrieves the weather data and processes it, and then writes it to the local machine that's being run. And then we also have the weather dashboard. This is just an example visualization of some of the data that's been formatted into the star schema. Selecting stations.py. For the purposes of this demonstration, I just used a couple of weather stations, 4 to be exact. And this program here pulled information from lots of weather stations and just selected a few that had quality data with good data coverage and also had the types of information I was interested in, like the min, max, temperatures, and precipitation. A CSV of the time dimension data and also the weather facts data table in a CSV. So a CSV of the formatted weather facts data, which is our main table. Okay, getting and processing the data. So that NOAA API data processing.py program does the following things. It gets the weather, station, and location data for a specified time period. In this case, it's 3 months, just for demonstration. Formats the data into the data warehouse schema, and then it writes the formatted data to those 3 CSVs. So this is just a snippet of code from the program. Getting the data, the token there has been removed just for the purpose of this picture, but you can sign up and get a token from the NOAA API documentation, and then you can include that in your code. In this case, the token can't be included as just an API key in the URL. It has to be included as a header. Those are the parameters for the request. So there is a hard limit on the API of 1,000 record to be returned. It won't let you return more than that. So you have to make a couple of requests if the data that you want has more than 1,000 records in it. You'll have to make a couple of requests. Station ID, that station IDs right there is just a list of different station IDs, specifically the 4 that we selected already to use in this demonstration. Dataset GHCND, that has our daily weather data that we're interested in. We can specify a start date and end date. Here we're specifying the data types we want. We want the min temperature, the max temperature, and the precipitation, and we want the data in standard format instead of metric. So there's our URL. We add the base URL, and then from the data endpoint, and then using Python and the requests library, request.get URL, add our headers with the token, add our parameters, and then I want to extract the JSON from that response object. So once we have acquired the weather data, we have to format it into the star schema format. So this is the function that does that, define process weather data. It takes the formatted weather data, extracts the results from the JSON, turns it into a pandas data frame. It also pivots that data because as it is, we have our data types in one column instead of in 3 separate columns like we desire. So our min, max, our min temperatures, our max temperatures, and our precipitation are all in one column. And then what field we're looking at is all in one column called data type. So we want to take those data types and make them each separate columns and then populate those with the data from the value column. So that's what the pivoting does. I'm going to reset the index. We're going to rename some columns. And then I just want to extract those, specifically those columns that we've renamed, because that's what our schema requires, the station ID, the date, temperatures, precipitation. Rename axis here, non-axis equals 1. When we do pivoting, it gives us a double layered axis, but we want to remove that and just have one row of column names. So that's what this does. And then formatted data, we're going to take the date that was returned. The date that the API returns has also a timestamp attached to it, but we just want the year, month, day. So we're going to strip the timestamp that we don't need from that date column. And then we're going to return the data formatted. So there's also some formatting and processing for the stations and the location, but you can go look at the file and the full report for more information. So data quality check, we'll just look at the weather facts table in this presentation, but there is some data quality checking for the other 2 tables. Python has some pretty simple or some easy to run built-in functions that make this quite easy. Describe and info. We can see here we have very, very good data coverage for the stations that we've picked in the time period that we've picked. So min and max temperatures, we have data for all 4 of our stations for every day in our 3-month time period. Only one station was missing 2 days worth of precipitation data. So near 100% data coverage, which is really good. We can see that all of our weather data values fall within the expected ranges as well. So take an example of the temperature min. The min temperature recorded was -4, max temperature recorded 64 with an average of 29, standard deviation of 14, and full 360 values. Precipitation, similar. Maximum precipitation, 3 inches, minimum precipitation, 0 inches, lots of zeros, just days when it didn't rain, mean standard deviation. So really good quality data, and probably helped by the fact that we intentionally looked for stations with really good data before running this example. This is just an example data visualization of what can be done with the data. This is Excel, couple of charts and slicers. We have some minimum temperatures fluctuating over time. We just picked a station here in the slicer. We want to look at this station here. Minimum temperatures as they fluctuate over time, maximum temperatures as they fluctuate over time, and then the precipitation on the days that it did rain. And this is a little chart showing our average min and max temperatures as well as some stats like standard deviation, etc. So what are the next steps? This is just a basic template for building off of when working with this data source. Some changes should be made to this main program that does the data processing. It needs better built-in error handling and retries since the API crashes sometimes. Sometimes when you run the program, it just won't work because the API says, I'm overloaded, I can't do it, right now, check back in later, and then if you rerun it, it will just work. So the program needs to have some built-in error handling and retries since the API crashes. We also have to have built-in data quality checks instead of just after the fact. If this is going to go into production and be automated, we're going to want to check for data quality as the data comes in and then send alerts when the data doesn't come in as expected so that this can be automated and not checked after the fact with that Jupyter notebook. So this is kind of a full production version or an idea for a full production version of what we could do. There's the external data source here, the API. We would pull that into our Python program to process the data. Ideally, this would be automated and running on some scheduled service like Prefect or GitHub Actions. In this case, we pick Prefect here as an example. So once this data is running in the cloud, automated, doing daily pulls of weather data, it would then send the data that it's pulled to a relational database. In this example, we just had, we would have a PostgreSQL database running on Amazon Web Services, and then we could have some dashboarding of that data that does automatic refreshes and pulls the data from our data warehouse. Thank you. That is my project. I hope you enjoyed it.